Hi, my name is Maria Hernandez, and I'm here today to talk to you a little bit about a very cool problem about pooled testing for COVID-19 and some mathematics that we can use with our students, basically from, say, middle grades all the way up through calculus. So what I'd like to do is share my screen and talk to you a little bit about the problem. Because we're not live, I will take some time to kind of just pause and think about, if we were together, how we could kind of approach this problem as a learner. And then I can share some resources with you at the end of the talk. So I will start my presentation by sharing my screen. Okay, so I traditionally have been for many years a teacher at the North Carolina School of Science and Mathematics in Durham. I retired in June of 2020, and I'm still working a little bit with COMAP as a mathematics consultant, which is the consortium for mathematics and its applications. And I'm also teaching a calculus course online. So I'm glad to be here at the ITSEC Conference virtually to talk to you about this problem. So what I'd like to do is share the problem and some background information. Also, like I said, kind of think about working together if you were using this maybe in your PLC, or if you're working with your colleagues or students, how we might stop and think about the approach at various levels, so that we're not just kind of revealing a solution, but instead thinking about kind of a modeling process. So like I said, the problem is accessible to students in algebra and pre-calculus, extensions for calculus, and actually you can take it beyond calculus of a single variable. I'll share some resources, and then again, think about the modeling cycle and where we are in that modeling cycle. So this is a modeling cycle diagram that comes from a modeling handbook that is a free download from the SIAM website. And SIAM is the Society for Industrial and Applied Mathematicians. So what we do is we start with a real world problem, or maybe just a real world scenario, and maybe students define the problem. And then they think about making assumptions, because in a real world problem, we can't just normally tackle the problem head on. We have to stop and kind of put some things on the back burner and make some simplifying assumptions so the problem becomes tractable. We define our variables, kind of spend some time in this brainstorming and research part of it. And then we get to a solution. That's kind of traditionally the mathematics part, where we work on using our mathematical tools to solve the problem. But because it's a contextual problem, we can stop and analyze our solution in the real world context. And then we might assess the model, or think about, is our model too simple and maybe not useful? So we might get kicked back into the modeling cycle, where we maybe change our simplifying assumptions or change something about our solution, and then come back out, get a solution. And eventually we have to kind of declare victory and get out of the cycle and say, okay, our model is good enough for now, because we can always improve upon our models. And then we'll report out our results. So as we all know, because of COVID-19, pooled testing is a very hot topic right now in the news all across the world. People are trying to figure out how we can test large numbers of individuals in an economical fashion, and also in a way that will minimize the time needed to get these results back. So because it's such a hot topic, it's actually can be very interesting to students to think about, how can we use the mathematics that we have in our tool bags to even think about tackling such an incredible problem. So this work comes out of some work that I've done with Usha Kadalawala and Lauren Siegel from Math Happens Foundation, and Usha from Developing a Math Toolkit. With the support of COMAP, we've developed some materials, and the materials are focused on kind of fostering mathematical curiosity with a demo, and then working through some of the mathematics and pre-algebra and introduction to statistics, and then developing models for a larger population. So that's going to be the portion I'm going to be talking about as the third portion, but I'm going to kind of give you an introduction, I guess, to the demonstration, so you can see how we might use a demonstration. So this is a demonstration kit that has like a rack here and some pipettes and some pH strips, and we can get these through Math Happens. I can, if you send me an email, I can forward that request to the Math Happens Foundation, and they can send one kit per teacher so that you could use this in your classrooms. And we have vinegar and we have water here. And I'm just going to show you a portion of this video. It's pretty short, actually. So I'm going to escape out of here, and I have it queued up in my browser. So this is the video that you can use with your students, and you don't really need the sound.
Hello, this will be in place of a live demonstration, but we're going to go through all the steps. Students, you're going to keep.
So Lauren talks about it, but what she's basically doing is showing you how the pH strip changes if we put water on it versus if we put vinegar on it. And then she's going to take 3 vials, and she's going to put some water in 2 of them and vinegar in 1 of them, and then shake them up. And then we're going to pool the samples. That is, we have 3 samples, and we're going to pool 2 at a time into 1 of 2 vials. She's going to show you how she does that. And then we're going to test just the 2 vials, not each of the 3 that are the individual vials in the back. So she's going to put tap water in the right one, and she'll have instructions for you if you want to do this exactly. You got to be real careful that you make sure that you don't mix up pipettes. And she's going to put vinegar in the back left one. And she's going to close up the vials and shake them up. And then she's going to test, she's going to pool the samples and then test the pooled samples. So hopefully we'll be able to figure out which of these vials has vinegar after she shakes them up and she pools the samples and tests them. And hopefully we'll only need 2 tests instead of 3. So we've just saved ourselves a test. Because we know what the pH strips will look like if there's any vinegar in the pooled sample, we'll be able to discern that. So you can show this video to your students, and then they can kind of figure out what's going on in terms of what is pooled sampling? What does that mean to pool samples? So she's going to take some drops from the back right one, which now we don't know what it is. And she's going to mix those with she's using a new pipette with some drops from the middle one. And so the first one on the right, far right, has samples from the 2 in the back on the right, middle and the right. She put a little bit from the middle in the left front vial. And she also put some samples from the back left one. So we have middle and right on the right, middle and left on the left. She's going to kind of stir them up a little bit. Well, yeah, just a little bit. And now she's going to test the pooled samples. So we can see the right pool and the left pool. And then this is where we stop and we ask the students to sketch some diagrams about what's happening here and which of the 3 vials in the back has vinegar in it. So this is an opportunity, if you're watching this with your colleagues, to stop and kind of collect that information from your colleagues and say, can you draw a diagram and tell me which one of these pipettes has the vials has the vinegar in it, and why. So if you wanted to pause here, you could do that. And we've done this with students and collected some sample student diagrams. And if you think about it, you can discern which of those 3 vials has vinegar in it just from using 2 tests instead of 3. So here are some sample diagrams that were done with students. One student did a Venn diagram. Some other kids just kind of looked at it in terms of the 3 little vials, and etc. So this is just a kind of a curiosity provoking, hopefully, exercise that you can do with, or demo that you can do with the students. So this problem comes, it's not a new problem. It's been a problem for a long time. And in the 1940s, the military was concerned about syphilis in the military population. And so in the 1940s, they were trying to come up with a way of testing many people for syphilis in an economical fashion. And so an economist, Robert Dorfman, came up with a way to do this, an idea for kind of, again, minimizing or at least bringing down the number of tests required. So this is just this is a different video. Right here, what we're going to do is we're going to think about 25 people in the population. And we're going to try to think about how we could save some money by pooling samples in a group size, and then just pooling those, testing those pooled samples. So this is a different video. And again, I have that one queued up. So this one's just a minute long. And we'll look and see how we might have a different kind of scenario with the racks. So what Lauren has done, these are not available for like just for her to give them to you, but what she's done is she created like this really cool rack that it holds lots of different samples, and you'll see that in just a second. So she actually used a laser cutter to create this rack, and she has all the samples in there. So she has 25 in here, and she's going to pool them straight down to the very bottom. So she's putting 5 in a group. And then she'll test the pooled samples. And she sped up the video so that we can see that there are 4 of the pooled samples came out clean. So we can get rid of 20 of our kind of candidates, and then we'll go back and just test each of the group members individually. So we can find the one sample that was positive, and we just saved ourselves from having to pool all 25. So that's just another example where, again, kids could just watch that video and say, oh, I get it. I only need 10. Why do I only need 10 tests? Well, I tested 5 group samples, right? And then because one of those groups was positive, I went back and tested those individually. And this is one of the scenarios we're going to look at and kind of create the mathematics around that. So again, we'll kind of go back to the problem statement. Suppose that you have a large population that you wish to test for a certain characteristic in their blood or urine. This came from the idea of Dorfman. And then later on, they used this idea of pool testing, for example, in the Olympics to find athletes who were doping. And we're going to test we'll test either positive, each test will either be positive or negative. And we're trying to figure out how to reduce the number of tests so we can reduce the cost. So we're going to take a minute to think about this in terms of kind of what information you might need. So this is part of the modeling process, right? It's a big real world problem. It can be daunting if we don't stop and think about what kinds of questions we might ask, what kind of information we might need, and also how to maybe put some of those questions on the back burner and say, well, I don't really know the answer to that question, but I'm not going to deal with it right now. Instead, I'm going to make some simplifying assumptions. For example, people have said, what about the efficacy of the tests? You know, how many false positives will we have? How many false negatives? What's the prevalence of the disease in the population? So again, if you want to stop the video and talk to each other about what kind of simplifying assumptions you might make or what kinds of questions you would have to solve this problem, you could do that. So we're going to kind of start tackling the problem. And again, kind of just thinking about the problem statement. And we're going to start with the idea is what's the relationship between that probability of an individual testing positive? So we might make an assumption about that our tests are very reliable. And we want to think about what's the probability of an individual testing positive and that group size. In that the example that Lauren showed us, we had 25 people and she made group sizes of 5, but we're going to kind of explore different group sizes based on that probability of person testing positive. So we go back again to the modeling cycle. There's a really nice resource in that modeling handbook where they have the modeling cycle, these different components described, and you might take those and make some laminated cards. I've had those before where I put them on the students' desks and we say, okay, well, what part of the modeling cycle are we in right now? Think about that. And so they can kind of get more comfortable with this idea of iterating a problem. They don't often have time to kind of iterate their mathematical solutions, right? A lot of times they get one shot at doing a problem, but hopefully they'll be able to kind of appreciate the opportunity when we're doing modeling that we get to stop and say, let's refine our model and make it better. So the simplest version of this problem could be thought about in terms of, like what's the simplest way that we're going to test everyone in a group and then test it the individuals who positive, right? So let's just go to the simplest of the simplest versions. So that was the idea that, again, Lauren demonstrated originally, was that once we had a group that tested positive, we're not going to do anything too, much more sophisticated than just going and testing each individual. But now let's just think about if we just had 2 people in the population. If we only have 2 people in the population, okay, and we're trying to figure out how many tests would we need, we might stop and talk to a neighbor about how many tests will we need if we only have 2 people in the population and we're trying to find people that'll test positive. Okay, so again, this might be a place where you stop the video and talk to each other about that. So after you've talked about it a little while, you can kind of ask folks about what they're thinking, how many tests will we need? There might have been some questions that came up. For example, I might think about like the scenario if they're both negative, if one is negative and one is positive, there are 2 possibilities there, and then if both are positive. And some people might ask the question, how are these tests conducted? Remember, we're taking 2 samples, we're going to pool them, and we're just going to test that one pool to start with. So at least we'll need that one test. And then depending on kind of whether or not that is positive or negative, we'll have to do more tests, right? So if you pool both of them and you sample that one pool sample and you get it and it's negative, then you're kind of in clear, right? Because you know that both people are negative, again, if you believe in the reliability of the test. So in that case, you'll just need one test. And if one person is negative and one person is positive and you pool their samples, the pool is going to be positive. So now the question is, when you sample the individuals, will you get some information from one before you have to figure out whether or not you need to sample the second person? If it is true that you could get some information first, then you might only need 2 tests. Because if your pool is positive and then you test individual number 1 and that person is negative, you could potentially say, oh, well, I know the other person is positive, and then you only needed 2 tests. But that rarely happens. They go ahead and sample both of the individuals. So in which case you would need 1 for the pool and 1 for each of those individuals. So that's 3 tests. And that's the case for all 3 of these scenarios, 1 negative, 1 positive, each of those, and then the both positive. So if we think about this simple case, we want to think about what's the expected number of tests, and thinking about a little bit of expected value in terms of mathematics. The event times the probability of the event is usually the way we calculate expected value. And by the event, I mean the number of tests needed. So either one test or two tests or three tests, depending again on that sequential testing possibility. And then the probability of each of those occurring. So if you think about our one test, this is our group being negative. This is if we had two or three. If our group was positive and then our first person was positive, then we would have to test again. And we would either get a positive or a negative. And then this is the other possibility, that if you could do this sequentially and you test and your group is positive and you test one individual and they're negative, and you make the assumption that the second person is the positive one when you haven't tested individually. So this is kind of cool because this is a function T, where T is the total number of tests based on the probability of a positive test. And so what we're going to do is we're going to calculate, this is an expected value idea. So we have one test, and what's the probability of only needing one test? It would be 1 minus P, which is the probability of a negative, squared, because that's two individuals negative. Then the case where we only need two tests, you would have two tests times 1 minus P, that is that the first person is negative and then the second person is positive. And then the other two scenarios are when you need three tests. One is positive and the other one's negative. And the other scenario is you need three tests if both people are positive. And then this is a quadratic polynomial that simplifies quite nicely and is kind of standard procedure in terms of what we study a lot of times in mathematics, is these quadratic models. So students know a lot about the behavior of quadratic functions. So we could take this model over to Desmos and graph it and think about the domain of this part of this particular function in this contextual problem, because P is a probability. So that's also very cool. Kids can think about like, what window does this make sense to look at? And then what's the total number of tests? So if I go out to Desmos, or actually I have a graph of it here. Let me just show you that. I have a graph of it here where this is the function, the total number of tests. And then I graph the line y equals 2, because y equals 2 is how many tests we would need if we didn't do this pooling scenario, right? So it might be interesting to think about, well, what would the probability be where our number of tests required for pooled testing would be more than 2? And that kind of threshold here is about 0.382. And so you can talk about that with your students. Like, what does this mean? I know this is a very simple scenario, but we got to start somewhere. So the other case is our kind of worst case scenario. That is when you didn't have that sequential idea, in which case you would need 3 tests for 3 of the cases, right? And so this function is a little bit different than the other one. In fact, here it is. I've graphed, I call it W for the worst case. So this is the worst case when that one's the green one. And this is our original function, the red one. And then there's my line y equals 2. And we could kind of say, like, what's the difference between these models? You know, should I be concerned about that sequential possibility? And the answer is there's not a big difference. In fact, you could graph the difference. So here I have, again, the worst case scenarios in green, and the red one is my original function. And then I just created a function, the difference between the two in Desmos, and I looked at the maximum. So this purple one is the difference between the green one and the red one. And you can see that these don't differ by much. The maximum is 0.25, that's the Y value, that's the number of tests. So this is kind of an important idea, even though this is a simple scenario, because oftentimes in mathematics, we think of the worst case. And if we can solve the worst case, then we have a pretty strong model, I would argue, because if you can come up with a solution for the worst case, then you've got a robust model. You've kind of tackled the tough stuff. And this will come up later. So now we're back to our problem of money and time, right? We got all these tests now. We don't just have 2 people in the population. We have more people in the population. So this was the original problem statement that I used to use with my pre-calculus students until I started diving a little bit deeper into this question and thinking about how can we help kids like really get their minds kind of wrapped around this big problem. So this is in a consortium article from COMAP. That's a free download from the COMAP site. And 2 of my former colleagues, Dot Doyle and Dan Teague, wrote a wonderful article about blood testing. And it contains a lot of the mathematics that we're talking about here. So if we think about, again, we're going to start defining some variables. We're going to say, what's the relationship between the probability of an individual testing positive and the group size that minimizes the total number of tests? Okay. So I created some materials for students to kind of like some warm up activities and some problems that you can kind of use in your classes to help the students kind of get their minds wrapped around this big problem. So let's just suppose we have 12 samples and somehow we know that there are 2 positive samples in there and we're trying to find those 2 positive samples. And we're going to start with a group size of 4. So what I do with this problem and what I hope for is that students will maybe just draw some pictures. Even I like to do it while I'm talking about it. We have 12 samples. We're going to have group sizes of 4. So we're going to have 4 in each group. That means we'll need 3 groups. And we're looking for 2 people that are positive or 2 samples that are positive. Okay. And remember this we're back to the simpler idea that if a whole group tests positive, if that pooled sample tests positive, we'll go back and test every single individual in the group. So this would be a time when, again, if you were here live with me, I would stop and ask you guys to think about how many tests will we need to find these 2 positive samples. So after you've talked about it with your friends, you might say it depends. And it does depend. It depends on whether or not those 2 positive samples fall in the same group. If the 2 positive samples happen to fall in the same group, then you'll need fewer tests than if those 2 positive samples, each of those samples might fall in 2 separate groups. That's kind of like they're spread out. And then that's our worst case, is if they're spread out. So this is really great because this is just a simple idea, but it gets to a very complex idea and students can understand it pretty easily. So for example, this is a sample student handout filled in kind of for the teacher materials. Here's a group, there's a positive person in there. Here's a group, there's a positive person in there. Here's a group, there's nobody positive in there. So because we had 12 people, group sizes of 4, we knew we had 3 pool samples for starters. So we have 3. Then we found 2 of those pooled samples were positive. So we got to go back and test every single individual in there. So that would be 8. So 8 plus 3 is 11. But somebody might say, oh, but no, if those 2 were in the same group, then we need the 3 to start with, and then we just need the 4 because we would test each individual in that group that had those 2 samples. So this, again, is a really nice idea to think about worst case and the kind of the range of values for these number of tests. In either case, we've used less than 12 tests, right? So we've saved ourselves something. So now as a class, what I had was I created an activity where we're going to have 30 people in the population, 2 positive samples. And we would do the same thing we just did now, but instead I would assign each group different group sizes, like the different groups of my students would each have a different group size for this scenario. So because we have 30 people in the population, we have lots of different possibilities. It's kind of cool. We could have a group size of 10. We could have a group size of 6 or 5 or 3. I mean, we could even have a group size of 4 if they wanted to check that out, right? But 30 is nice because it has a lot of divisors. So what students will do is take their group size and work with their classmates to figure out how many tests we'll need for each of those group sizes. And then we'll, I want to say pool, collect all that information, and it'll be a data set. It'll be a data set that'll talk to us about how many tests we need versus what the group size is. Okay. So that, again, if you wanted to stop and do that with whoever you're working with, you could do that, or you could do that with your students. So this is just an example. I'm showing you what happens. My probability of testing positive is 2 out of 30. And these are my different group sizes. And then students can see that if your group size is big, you're going to need a lot of tests. If your group size is small, you're going to need a lot of tests. Somewhere in the middle, there's a minimum number of tests that you will need based on the group size. So this is just a sample, like I said, 10, 6, 5, 3, 2. If we graph this data as group size on the horizontal axis and total number of tests on the vertical axis, this is what it looks like. So students might try to connect those dots. They might say, oh, have I found the minimum? Well, these two are 16. These two group sizes yielded 16, but maybe I'll try 4 and see what happens. The other thing that's really interesting about this is that we have discrete values, right? We're talking about integer values for our group sizes and integer values for our total number of tests. So we might leave this kind of discrete and move to the continuous by saying, could we come up with a model for this, like a function that that spans across this particular domain? So for the domain, we could say, oh, well, our total number of people in the population is 30 for this particular example. So we're looking at this function over a limited domain, a domain of reality, if you will, and then think about the possibilities for the total number of tests. So that's what we're going to do now. We're going to try to create a function for the total number of tests. And we already noticed, again, if you've played with these numbers and kind of explored them, the kids notice right away that the groups, this number of group tests depends on the size of the population and your group size. And then the number of retests depends on how many people are sick or how many vials will test positive, right? And where they are if they're spread apart. So we're going to think about the worst case and think about those individuals who are positive being spread across those groups. And then we can think about like how to come up with an expression for those number of retests. So we have the total number of people in the population, which was 30 for us. The group size will vary. And that probability of a positive for us was 2 out of 30, okay? So if you think about the number of first round tests, we did that right away when we did our example, right? We said total number of people in the population divided by the group size. And then this is kind of interesting, that probability is 2 over 30. I might even leave it as 2 over 30 and not write it out as 0.067, because we'll see something interesting in terms of this number of retests. So our total numbers of our first round is 30 over G plus our number of retests. And our number of retests is really kind of that expected number of values of positives, which was 2, right? So we had this 30 times 0.067, but that's just the expected number of positives times our group size. So I think we have our model, right? We have these 2 people that were sick times the group size, because you're going to have to go back and test each of those individually. And again, we could graph this on Desmos along with, or our graphing calculators, whatever graphing tool you use, along with our data set. So there it is, beautiful. And then again, we can find the minimum. The minimum is in terms of non-integer values, but again, that discussion of discrete versus continuous is rather interesting. And then we can think about how can we expand this for larger populations and different probabilities of positives. So what I have here is I've created a model that's more general in terms of the population size. It's still a function of G, so there are lots of what look like variables kind of swimming around in this function, but many of them are parameters, right? We're getting the total number of tests based on our group size, but N is the population size, that's a parameter. The probability of someone testing positive is also a parameter. We don't have control over that, right? That's P, some value P. And so if we look at this is rather interesting. It's still our rational function, and again, a great application of rational functions, N over G, plus this NPG, which is the total number of people in the population, times the probability of testing positive. That's our expected number of people testing positive, times the group size. And that's that idea that we go back and test everybody individually. And what's really cool about this too is that if you factor this N out here and you just look at this function, this n will just be like a vertical stretch, right? So if you wanted to even simplify the function more, you could say, well, let me just look at what's going on this one with 1 over g plus pg. Okay, so let's think about kind of some relationships here. We have a couple of different things going on. We have originally we just changed the group sizes to think about how many tests we would get and what was the optimal group size. But it also depends on this probability. Remember, on these scenarios I've given you, I've told you that there were 2 out of 30 or 2 out of 12 or whatever positives. And so what we'd like to do is really try to think about how we can find the optimal group size for various p-values, because we don't have control over that. So if we do that, we can collect a set of data that will help us kind of understand this relationship between this optimal group size and the p-values. So let's think about how we might do that. So here's my function, and I just chose a p-value. P-value is much bigger now, it's 0.25. Okay, so I said, if I look at this function, and again, I'm just ignoring the n, because the n will just be a vertical stretch of the function. So the minimum of t and the minimum of my kind of modified t will still be will still occur at the same value. It's just the y value will be different in terms of the number of tests. So if you look at this and you choose a particular p-value, this is another activity that you could do with your students. You could say, if we're in groups, I'm going to give each group a different probability value. I'm going to ask you to give me what is the optimal group size for your value of p. Okay, and that will vary. So for example, the optimal group size is 2 if the probability is 0.25 for this particular case. Here's a different one. If the probability is much smaller, 0.01, the optimal group size is 10. So now we can collect a data set and see what's that optimal group size based on the probability of someone testing positive. And this is really great. You get this data set where my X values are probabilities of testing positive, and my Y values are optimal group sizes. And it has this really incredible relationship here that looks like a power function, where the power is less than 1, actually less than 0, right? It's because it's 1 over some X to some power. It looks like it. So if you are studying statistics, for example, or if you teach this in your pre-calculus course, you could think about re-expressing this data, because if you think the data is best represented by a power function, you can do what's called log-log re-expression and actually trying to find a model for this. Or if you aren't studying those particular courses, but instead your students know about 1 over X to some power, they can take this data set and they can explore what the power of that X would be, in which case they could use parameters in Desmos and kind of look at sliders, or they could also do some regression analysis just by using some technology that does regression for you for a power function. So the beautiful thing is that the function for this is 1 over the square root of p. So let me go back. This function looks like a 1 over X kind of function. It's actually 1 over the square root of X, but remember p is the probability. So this best group size depends on the probability, we knew that. And in particular, that dependence, the best group size, is 1 over the square root of p. So if I take my total number of tests and substitute in 1 over the square root of p, I can tell you how many tests I will need. It will be, if you simplify this algebraic expression, you get 2 times the total population times the square root of p. So if you know that your probability of testing positive is, say, 0.1, you can put 0.1 in there, you can multiply by the total number of people in your population by 2, and you can see how many tests you'll need. So this is really cool, because now I have a way of saving money and tests if I know the probability of testing positive and the total number of people in my population. So for example, if I had 100 individuals positive in a population of 1 million, It'd never take more than 20,000 tests. I'm going to take a breather there, just a second. And of course, you can stop the video and kind of think about it. I know I'm going through it fast, but I've done it a lot, and I'm very excited to share the mathematics in the problem. So the next question that we pose here is to think about, for what p-value would it be useful, not be useful to pool samples? Because we saw that, right? If you have a really, well, if you think about it, if you have a lot of people who test positive, then you're going to have to go back and retest a lot of people. So there must be some threshold where if the probability of positive is bigger than some number, we shouldn't use pool testing. We should just test everybody individually. So the beauty again of this is that it has all of this mathematics is accessible to high school students. And we can try to answer that question. And that is like, when is this total number of tests going to be bigger than n? Because n is the number of people in our population. So that's just an inequality, right? 2 times n times the square root of p. When is that bigger than n? There it is. When is 2 times n times the square root of p greater than n? For what p value? Well, luckily the n's divide out, and we actually get a value for p. That if the probability of testing positive is bigger than 1/4 or 0.25, you shouldn't use pool testing. So again, very, very important result. So if we want to think about using calculus, really there's not a whole lot of difference here, except that when we get to creating the function with our parameters, we can do the mathematics a little bit quicker, right? We don't have to do all these different kinds of analyses. But we often say at the School of Science and Math that it's really powerful to do modeling problems at the same modeling problem at various levels of mathematics, of the mathematical courses that students are taking, because you can do this problem in a pre-calculus course, and then you can revisit the problem in a calculus course, and students can kind of see that as we know more mathematics, as we build our mathematical tool bag, that our solutions can be kind of more complex. We can deal with things more in terms of parameters. We can kind of get to a solution a little bit, quote unquote, quicker based on using these more sophisticated or more complex tools. So this is just an example that we could take the derivative of this function, set it equal to 0. We can get our g value like right away by doing that in terms of a parameter. And then of course we could test to make sure that we've really minimized the function using a first or second derivative test. And then we can also go back and stop and say, you know, this model is limited. Assume that we would only group test once and then test individuals. Could we do better? Maybe students already thought about this and they had to kind of put this idea on the back burner and say, wait, why do we have to test every single individual? Can't we do something a little bit more complex with our group that tested positive? Can't we like subdivide them into groups? So that's a great question. And it's a question that as you see, we've put on the back burner for this particular presentation, but the article that I'll share with you that you can get as a free download from COMAP, that consortium article kind of goes into that idea. So I really love mathematical modeling. It gives us a chance to amplify students' voices. We aren't the ones that are always kind of, you know, leading the conversation. They get to think about some real world problems and how the mathematics that they're learning can help us as a society solve some really big problems and make life better in a sense, right? For individuals, especially right now when we're tackling so many huge problems. So it gives the students a new lens through which to view mathematics, that mathematics is not just something that we do in school where we push symbols around, but we also use it to inform ourselves as individuals and our society in general to solve some big problems. So here are some possibilities for some resources. If you do want a lab kit, we can send one to teachers. I can check and make sure we still have some from Math Happens Foundation. You can send me an email. The game report is a free download from the SIAM website. That's the Guidelines and Assessment and Instruction for Math Modeling Education. It's a wonderful publication that gives you ideas from elementary school all the way up to college level for kind of dipping your toe into modeling, or maybe even maybe you're already doing modeling and you want some different ideas for mathematical modeling in your classroom, including some rubrics to think about how you assess student work. So that's, I know, always a big question, like how do you assess students when you're doing these big real world problems, and thinking about the modeling process. There's a math modeling handbook that I showed you the diagram from. There's also the COMAP consortium article, Everybody's Problem, blood testing. And then Mathematics Modeling Our World actually had versions of this problem and some of the mathematical tools in there in terms of the curriculum in their Modeling Our World curriculum back from 2001. So they had already thought about this problem in particular for the Olympics and testing athletes. We have a conference at the North Carolina School of Science and Mathematics, which is called the Teaching Contemporary Math Conference. It's coming up in February and the registration is open now. You can send me an email if you want more information, or you can just Google it, NCSSM TCM. That's in February. We're going to have some people here in Durham on campus with a limited number. We'll be also having some remote attendees. So if you're interested in attending that remotely, or if you're interested in coming in person, you can register. And then the Anya S. Greer Conference at the Phillips Exeter Academy. I've taught workshops there for several years, and they have some wonderful workshops, and that conference will be coming up in June, and the registration will be opening soon. And then we're also having some more pooled testing workshops. I'm going to be offering this one, but my colleagues, Usha and Lauren, will be offering their versions. That's a free workshop on December 7th and 8th coming up. So if you're interested in that, I can give you a link to that to where you can register. And then, of course, there's the COMAP modeling contest for your students. That's a wonderful way to have students work with each other collaboratively to work on some big real world problems. And those are for middle school students, high school students, and university level students. So that's a great resource for you to kind of check out. So I thank you all very much. And I thank COMAP for supporting me in this work. And I hope that these materials are useful for you. And if you have any questions, please send me an email. I'm happy to send you links to resources or to any of these other things that I've chatted with you about. So thank you very much. Thank you, ITSEC, for inviting me to present.